Well, I've got some bad news, but I guess some good news too. The bad news is that we have to talk about stoichiometry again, one of the least favorite things that students have ever experienced. But the good news is that this is really the last skill set that we need in order to be able to attack any kind of problem in this like balanced reaction world that we live in here. So honestly, the first thing to always remember is that your moles are what matter, right? And so anything that you see in terms of a stoichiometry problem is always going to involve some sort of dimensional analysis that converts something into moles. So let's just remember that all of these things are all based on this kind of generalized idea that what a balanced chemical reaction is telling us is just some sort of recipe for making a certain product, right? And so we could say 2, 3, 7, and 1 or something like that, right? And so the whole idea of stoichiometry is this mole bridge concept that says that we have to take anything that's given to me, turn it into moles so that we can use these numbers to, I don't know, to try to determine how much reactant I need, how much product can be formed. So all of these are going to involve really the same steps we've now talked about 2 different times, right? Way back in 104, which seems a million years ago, we talked about how to take grams of something, turn it into moles, yada, yada, yada. Now what we're going to do is we're going to take that molarity information from Friday, keeping in mind that all that molarity is, right? And I'll write it out one more time. It is, of course, a measure of concentration, which is the number of moles of something in liters of solution, right? So what this tells me is that if I am given, let's say, the number of liters of something and its molarity, and I can convert that into moles, which we kind of did in the video lecture on molarity, then I can have a whole new way to convert things into moles, right? And of course, I could change up the problem a little bit, and I could say maybe I used this many mils, and I had this many moles. What was my molarity of the original solution, right? But all of it really has this mole bridge concept all kind of packed in there, right? What do we need? We need a balanced chemical reaction. We need some way to convert to moles. So what I'm going to do is I'm going to go through a couple of your homework problems, which are going to be available on the resource guides for today. And on that resource guide, there's going to be a little section that kind of guides you through kind of a dimensional analysis way of doing these things. It was kind of confusing to me, but some students in the past have found it pretty helpful. But I'm just going to kind of pick out a couple of questions at random, and I'll go through them with you, and hopefully with that as kind of like something to help you through the rest of the problems. Hopefully you'll be able to finish the whole thing. Yay! Okay, we're jumping right in with number 1 from that sheet. I'll hopefully include a screenshot of that thing right there. So how do I know I'm in a solution stoichiometry problem? Well, friggin' there's going to be some information about molarity. It's either going to be provided or asked. And then there'll be some sort of balanced chemical reaction that I kind of wrote on 2 lines here. And so keep in mind, I need a balanced chemical reaction, right? So a lot of these are not going to be balanced to start off with. So that's the first thing I'm going to do here. And I'll draw it in blue, so hopefully you can see it. So we go la-di-da-di-da, right? We're going to have to put a 3 here, a 6 here, a 2 here, and a 2 here. And I'm pretty sure that that sucker is balanced. I better check to make sure, otherwise all the work I'm about to do will be totally worthless. So hopefully this thing is balanced. Next step, what I'd like to do is map it out just like we did with the gas stoichiometry type problems. So let's see, what is my given information? I am being asked about the grams of aluminum, right? And so that's kind of my output arrow there. Question mark. And I have been given 35 mils of a 2 molar hydrochloric acid solution. So there's my hydrochloric acid solution. I've got 35 mils, and it is exactly 2.0 molar And so let's attack this question straight off here. Well, what are you going to do? Well, it's a reaction stoichiometry problem. You're probably going to convert to moles. One of the most helpful things, which I did in the molarity lecture that I think will hopefully be helpful here, is that I don't like to write molarities as that big M. I like to remind myself of what the heck that thing actually means. And so what this is telling me is that I have exactly 2.0, I hope that was 2.0, yes ma'am, I have 2.0 moles in, well, let's not put equals because that's even more confusing, in 1 liter, right? That's what moles always means. So there's my mole amount, right? I know that I can somehow use this to determine moles. Well, what I have is 35 milliliters. So the first thing I'm going to do is in my head or through dimensional analysis, in my head, stop it. I know I have that many liters of an HCl solution. I'm going to treat this like I've treated every single dimensional analysis in the universe. I'm going to do it stepwise. I know that I need to go to moles of something. I'm going to go to moles of HCl. I'm going to say, okay, what units go where? Well, I know that I want liters here. I want moles over there, or on top rather. And then this, because I've written out what that big M means, it tells me where my numbers go. And then I say, okay, I reminded myself that I can use molarities, multiply them by volumes in liters to end up with some number of moles. And I'm pretty sure that even I can do this in my head. It's a dangerous time we live in here. So I've got 0.070 moles of HCl. Guess what I'm going to do? Just like I've done every single other stoichiometry problem before, I have to convert that moles of something into moles of something else using the balanced chemical reaction. And I've got my 6-to-2 relationship right here. Just so my brain doesn't hurt, I'm going to just go ahead and write it out in a separate step. I know I have to convert the moles of something into the moles of something else. So it's going to take a conversion factor. This is going to be over 1. And hopefully you can even see what I'm writing. What an excellent thing that would be in a video lecture. And I need to go to moles of Al, right? Because I want to go to grams ultimately. So I'm going to go to moles instead because I can't go to grams immediately. See my units, moles of HCl. I see moles of Al. I look up and I see what number goes where. I see that the 6 goes with HCl, the 2 goes with Al. And I say, well, is there anything I can do to simplify my life? Well, I guess a little bit. That can go to 1, that can go to 3, right? So I'm going to take that 0.070, divide it by 3, and I've got my moles of Al. And at that point, you should be like, aha, I know what to do. I've got moles. I need grams. We're going to multiply by the molecular weight or formula mass or molar mass or whatever you want to call it. So hold the phone. Okay, so I plugged it into my calculator. Hopefully this thing works out to 0.0233 repeating for you too. I keep track of my sig figs just because I'm a mindless automaton that can't stop himself. And I'm going to erase this and do the very next step, which you should feel oh so comfortable with by this point. All right, I'm feeling good about this. Got moles of Al. I want to go directly to the grams of that thing, which I know I can do in one step. I've got moles of Al. I've got grams of Al. I look up on the periodic table what the heck that thing is, which I should probably do a better job of. I think it's 27 something, but I better look that up. Okay, well, I guess I remembered wrong. It was 26.9815 off of the periodic table, which means that I can get my units to cancel, and I do that multiplication, and I end up with my final answer. Okay, so I've got my 0.6295 grams of aluminum, And I am going to round that to my final answer, which is 0.63 grams of aluminum. We don't need a question mark anymore. That's how you do it. Well, guess what? You could have taken this exact same problem and set it up exactly the same way with this 35 mils of 2 molar HCl. And instead of asking for the grams of aluminum, we could have easily asked for the grams of aluminum chloride produced. We could have asked about, given standard temperature and pressure, or maybe not standard temperature and pressure, how many liters of H2 gas could be formed, right? And so those are the three big ones, right? The three ways of using stoichiometry. You can either use solution stoichiometry, you could use gas stoichiometry, or you could use just the normal gram to mole stoichiometry. So let's try a couple of more. Hopefully you'll notice it's the same exact thing. Okay, so this one's just a little bit different because it's going to be asking for the number of milliliters of something required. We're going to map it out in the exact same way. First step, as always, is to make sure that this sucker is balanced. And we'll do this in blue. Kind of a similar balance to the last one, I guess. 2 of these and then 6 of these. Let's see. Okay, I think that checks out. Now we'll see what they are requiring of us here. So how many liters of a 3 molar H3PO4 solution? So at the end, I want this to tell me the liters of a 3.0 molar solution, H3PO4. Okay, so that's our question mark. Our input is that I have 4.5 grams of zinc. Well, as always, I'm going to convert to moles, right? Use those moles to convert to the moles of this. And then I'm going to see how I can manipulate this whole molarity to give me the number of milliliters. Is it asking for milliliters? Sorry, liters of something. So volume of a solution. And the first thing I'm going to do, because I think this is super helpful, is to write the fact that that is moles per 1 liter. Okay, let's set it all up. Well, not surprisingly, I've got 4.5 grams of zinc over 1. I'm going to convert this thing into the moles of zinc. And by the way, keep in mind that you could do all the steps that I'm showing right here as one big giant dimensional analysis, but that's not usually the way that your celebration or fiestas of knowledge are going to happen. So I'm going to do it nice and stepwise here and get all kinds of partial credit from myself. What are you doing? Grams. Okay, and so let's look up the molar mass of zinc, which I do not remember. All right, so I've got 65.38 for the molar mass of zinc. I'm getting that off the internet, so hopefully it's okay. And we'll do our conversion. Grams of zinc crosses out with grams of zinc. We've got moles. Woo woo, we've got moles. Okay, so here's our mole bridge step. We're going from moles of one thing to moles of something else. I keep writing smaller and smaller, so it probably gets worse and worse. We got 6 that goes with the moles of zinc. I've got a 2 that goes with the moles of H3PO4. This simplifies just like it did last time to a 1:3 ratio. We've got our 0.02293 moles of H3PO4. And now let's put this up here and we'll kind of see how we might be able to use this information to determine the number of liters. Okay, there's the setup of the dimensional analysis. So we got moles of H3PO4 and we want to go to liters of H3PO4. notice what the molarity gives us, right? We know that there are 3.0 moles in every 1 liter. That's why I like to write out molarity, because if that was written as a big M, it just makes my brain hurt. So I can tell that, well, my 3 is going to go with the moles, 1 will go with liter, and so we should end up with just dividing that number by 3, and we are nearly at our final answer. And there's our answer to the question. We are going to write it rounded up here. So we have 0.0076 liters of H3PO4. Now, one of the things you'll probably pick up on as you work through this homework, sometimes liters is okay. Other times we're going to convert to milliliters. All you'd have to do to convert that into milliliters is, of course, move this decimal point 3 points to the right. So we end up with 7.6 milliliters if you're into that. We're going to do one more together, and then I think that's going to be enough coupled with office hours for everybody to feel pretty good about this. Okay, so we're back to question number 8 here. Honestly, there is one more page to this that says slightly tougher stoichiometry questions. The only thing that makes it really tougher, though, is the fact that you're going to have to come up with the chemical reactants and products, right? And so you might have to look back at some of your naming rules. The reason I wanted to end with this particular one is that when we get to acid-base chemistry, which is the very next topic, we're going to be doing a lot of this kind of manipulation. This is called the neutralization reaction. What we're doing is we have an acid and a base coming together to form a salt and water. This is going to be a really, really common type of stepwise process that we're going to have to do in labs and such, having to do with this. So I just figured I'd throw it in here. As always, what we're going to do is make sure that we have everything balanced to start off with. Okay, so once again, I apologize if you hear the dog barking, but I can't get her to stop, so the heck with it. We've got our balanced chemical reaction now. We're going to map it out just like we always have. I know that I've got 525 mils of a 0.8 molar HCl. 525 mils of 0.8 molar HCl. And ultimately, I want to know if I neutralize something with 315 mils of this, what is the molarity? So let's see if what is that? Question mark. Okay. So let's see if we can put everything together. One of the things you'll notice is the very last step looks a little bit different than the last step of the 2 that we just did. But let's go through and do what we know we can do, which is to convert this into the number of moles of HCl. Okay, so I set everything up that I could. I know that I've got, oh, by the way, I did convert that to 0.525 liters, right? Because molarity is always in moles per liter. That also tells me where to put my 1, where to put my 0.8. I've got 0.42 moles of HCl. I'm going to convert that into the strontium hydroxide. I am going to keep track of the numbers, right? I've got 1 with strontium hydroxide, the 2 with HCl, so I have to take this and divide, which I think I can even do in my head. I've got 0.21 moles of strontium hydroxide, and now let's take a look at the question that's being asked, right? I know that I've got that number of moles of strontium hydroxide. I know that it was supplied by exactly 315 mils of volume, right? So molarity is moles per volume, right? Let's write that down. The molarity of something is always the moles per liter of something. Well, what do I have? I've got exactly 0.21 moles. I've got 315 milliliters, which I have to convert to liters, like so. And you'll notice that it's not really a dimensional analysis, right? It's just plugging into my definition of molarity. I do that division, and that tells me my molarity. It's somehow appropriate that the sign of the beast has appeared. So we'll round this thing based on the 2 sig figs. Maybe I should put it was technically 0.80 moles, so ultimately it carries through to 2 sig figs. So the new molarity is 0.67. So as I said, really common type of problem that we'll have when we get to acid-base chemistry. The only part that was a little bit different was that very last step. So take a look at those worksheets, ask me questions if you have them,